In this course, we're going to cover an introduction to Java, the characteristics of Java, current technology, embedded Java, using precompiled applets, Java technologies, and future technology. Intended audience are IT managers and professionals, internet and intranet developers, and other business and IT professionals involved in the development of web pages and applications.
Everywhere from desktops to the server.
Components of technology that can be put together to solve problems.
The multiple environments, the heterogeneity.
Year 2000 crisis.
Solving that software distribution problem.
Everywhere from small businesses to the Fortune 500.
The tools are changing.
The boundaries between pieces of software.
Welcome to the course Java Principles and Applications. I'm Troy Downing with WebCal Corporation and with New York University. Our agenda for this course is an introduction to Java. What is Java, the programming language? What is Java, the runtime environment? The characteristics of Java, what makes Java unique? Current technology, how is Java being used? How is it being deployed and exploited? How to embed Java into your web pages or your internet applications. Using precompiled applets or finding applets that other people have created that you can customize and make your own. We're going to talk about Java technologies, what makes up the language, the object model, what really Java is about, and finally future technology, where it's going, what's coming down the pipe. First of all, Java can be explained in two parts. There's Java the language, which in and of itself is just a programming language. It's a very nice one. It's simple and powerful, but essentially it's a programming language. What really makes Java interesting and unique is the Java runtime environment, which allows you to run code that was created from this Java source code on a number of different machines. So one of the strengths are you have a homogeneous runtime environment that's running across a heterogeneous platform or a lot of different types of computers. You have a simple programming language. Very simple. It's easy to get up to speed when you're learning Java. There's built-in memory management or a garbage collector, which frees the programmer from having to meticulously worry about when memory is allocated or freed. There's built-in threads, essentially language support for multi-threading, which is a very powerful tool. Finally, Java compiles into a very compact form that's really built for network distribution. Some of the weaknesses of Java, first of all, it's semi-interpreted. By interpreted, I mean the language is interpreted from a source code, which is very similar to English or human readable, into machine code, which any physical CPU, such as a Pentium, needs to read to execute code. In Java's case, instead of having a high-level interpreted language or a low-level targeted machine code, you have something in the middle, which is a binary format that is interpreted into the native machine code. So it's faster than a purely interpreted code, but it's not as fast as native code. And since it is interpreted, it runs slower than native code. There's lots of checking in Java. There's bounds checking, types checking, access checking. These are things that add value to the language, but come at a cost. There's a performance hit. So that could also be listed as a weakness because it causes your code to run more slowly. One other weakness is that it's very easy to reconstruct source code. Since the Java binary code format is well defined, it's really easy to turn that back into source code, which can be a problem in a lot of shops. To really understand why Java is the way it is, it's important to understand the history and what it was developed for. At Sun Microsystems, there was a project called the Oak Project that had the task of developing a program and development environment for personal digital assistants, electronic devices, smart appliances such as set-top boxes and smart telephones, and smart homes. There's a lot of properties that go with programming and developing for these types of environments. They have very specific needs, such as the need for central control. And central control means that you need some sort of network distribution, some way of communicating with these devices. They need to be robust. It needs to be a very robust development environment and runtime environment when you're dealing with all these different types of appliances. There's also the problem of hardware heterogeneity. You have different types of embedded controllers in all these different types of appliances, and you need to be able to address that in your development program as well as your runtime environment. Security, it's obvious that you need security when you're dealing with these types of devices. It needs to be fast and simple. So James Gosling at Sun developed a new programming language. He looked at the offerings out there and wasn't really happy with C++ or C or Smalltalk, so he decided to develop his own. So he took an object-oriented model and he simplified a lot of the constructs that made other programming languages overly complex or difficult to read or use, such as pointers and multiple inheritance. He also made this a very robust programming language.
At Sun Microsystems, James Gosling, Bill Joy, and John Gage discussed the birth of Java and how Java simplifies the object-oriented model of C++.
We began this as, in some sense, a television operating system, except the television people didn't fully understand the power of computer languages running inside a TV set.
Oh, they did. I mean, it was a more complicated situation than that.
I mean, they had no money to spend on memory.
They wanted to control the universe.
I see. Well, now, does Java allow anyone to control the universe, or does it decontrol everything?
Well, one of the things about Java that's sort of unsettling to some people is that, I mean, the real intent was all around sort of open systems. You know, if you look at say a web browser, right? In a traditional web browser, you've got text and you've got images, and that's it. With a web browser that lets you put applets in there, you can put anything you want in the page.
So what's the fundamental idea that makes it so much simpler than C++?
Well, I don't want people to think that the language is a lot different than C, and it's not. But what it lacks is the complexity. And so if you're a C programmer, I think this is one way of looking at Java. It's C. In other words, we have the syntax, the semantics, and the expressions that you're familiar with.
Okay, so let me move this over a bit so we can see it. All right.
And then we've added classes, which are every entity, every variable is of a class, basically. All
So
the
we
types.
start with C, we add classes.
That's the Simula 67 concept, but we had garbage collection and threads. So they're managed automatically, more like you traditionally see in a Lisp system, where storage is automatically allocated, and concurrency is in the language, so it can be done correctly.
So that's the threads.
Right. Then we've taken two major things out.
I'm going to put garbage collection in here in big letters, okay.
We've taken out what I call unsafety.
Unsafety.
Yeah, I mean, we've added safety, but relative to C, we've taken out pointer to anything, free, which just says, I'm freeing this. Well, how can you be sure? Because something else may still point to it. And we've also taken out what I call on structure, which is what happens with C, where you run your program through the preprocessor, and thereby what the compiler really sees and what you see are just arbitrarily mangled from one to the other. So
on the unsafety, elimination of pointers and pointer arithmetic, free.
Yeah, that's manual deletion.
Manual deletion,
right.
Get rid of that.
Right,
Okay.
and the preprocessor, and also the notion that there's a header file, and then there's the code which goes with the header file. Those have been unified, so that simplifies things because there's only one definition of a thing. So it's actually a relatively small change, and people who've written C code like this, and I think will become fluent in it very quickly, because you don't have to master the arcana, and that's really important for people to be, fluent or literate in the language.
So we have this new programming language that's platform neutral. It's object-oriented. It's secure. There's language support as well as runtime environment support for security. It's very simple. It's easy to learn. And it's a very robust programming language. And this new programming language is Java. Java, a simple, object-oriented, distributed, interpreted, robust, secure, architecture-neutral, portable, high-performance, multi-threaded, and dynamic language. That's a quote from a white paper on the Java language. It's quite a mouthful, but I like quoting it because it really does live up to most of the things that it's saying there in one way or the other. So let's talk about the first part of that, platform neutral. What that means is that this works on a number of different hardware platforms. It's not programmed or written to run on any individual one. And the second thing, and this is a very important thing about the entire Java model, is that Java is binary portable as opposed to source portable. What that means is that you can compile a program, and once that program is compiled, you can move that from machine to machine, rather than having to recompile it for a number of machines, which is normally the case. Such as in C, which it's often said that C is source portable, which is true, but you still need to compile it for these different machines. I'm going to talk a little bit now about the Java virtual machine, which is really at the core of this. This is what makes this entire model work. First, a definition, bytecode. Bytecode is the binary representation of a Java program once it's been compiled. Essentially, you have the source code, you run that through a compiler, and you have the binary bytecode. This bytecode is then executed by the Java virtual machine. The reason it's semi-interpreted is the Java virtual machine then interprets that bytecode to the native CPU that it's running on, such as Motorola or Intel or a MIPS CPU. Another property is that a Java virtual machine, or any virtual machine, is a software implementation of a CPU, or central processing unit. What this means is that you have well-defined types. The integral types are well-defined. The byte ordering is well-defined. So as a programmer, you always know exactly how much space an integer takes up. You always know exactly what the byte ordering is of a floating point number, and you know the representation of these different data types. Java is an object-oriented programming language. It borrows from a lot of popular object-oriented programming languages such as C++, Smalltalk. It borrows from C. It borrows from these languages, but it's not exactly any of them. It's an easy model for distributed programming applications. It was really designed for developing distributed programming applications. It compiles into very small components. The objects can then be loaded as needed over a network. There's a very simple distribution for dynamically bound applications. Dynamically bound means that these applications are actually bound at runtime, which means that you can make changes to code to some small object, some piece of your code, as the application is running if it hasn't actually loaded that piece yet. It's bound when it's actually needed. Java is also secure. There's a number of security mechanisms. There's language-based security. And some of the constraints in the language-based security are no memory access. You don't have arbitrary access to memory. It's strongly typed, so you can't replace an object or a variable with something that doesn't actually belong in that spot. It also has configurable security managers for resource protection. What this means is that you can create a security manager that allows or disallows access to network resources, to local file systems, to anything that you could conceive of, really, that you would want to protect from anonymous code. There's also bytecode verification. Bytecode verification verifies that the bytecode is actually valid Java, because it is possible that somebody could create their own compiler to compile something that looks like Java but isn't actually. And so you have this verification that not only checks that it is valid Java code, but it also makes sure that it doesn't circumvent any of the other security measures, such as the strong typing. You also have something that I like to refer to as semantic bug security, and you get this with the typing and the basic structure of Java, meaning that it's harder to accidentally write code that can be damaging or insecure or open your system or your network to problems. It's also a very simple programming language. It's an easy language to learn. There are very well-defined operations. There's no pointer arithmetic. Actually, as I mentioned, there's no memory access at all. There's no pointers. They've gotten rid of pointers, which is actually a much easier model for programming. There's no operator overloading. This causes a lot of problems when you're looking at code that's been written in a language that allows us, such as C++. What that means is that it doesn't allow you to redefine standard operators. And there's no multiple inheritance, which is also another thing that can cause C++ code to become unwieldy and difficult to read. It's a very robust model. It has automatic memory management. It's got a garbage collector that runs as a low priority thread. It looks to see once you're no longer needing some memory access, some chunk of memory, and it automatically frees that up for you. No more memory leaks. It takes care of it for you. It's a wonderful thing to have. There's very simple multi-threading built into the language. You don't have to learn another threads package. It's actually built in, so it's very simple to write multi-threaded applications. There's no memory leaks, fewer bugs. These all contribute to the robustness of the Java model. I want to talk briefly now about the Java runtime environment. The Java runtime environment has basically three components. The first component is the interpreter. And what the interpreter does is this handles the actual execution of the bytecode. Essentially, your compiled Java is run through this interpreter, and each piece of this file is an instruction for the Java virtual machine. The second part is the bytecode verifier, which does all the checks to make sure that the code really is valid Java code, to make sure that it's not doing anything that's illegal in the Java model. The last thing is a class loader, and the class loader is what allows the easy network distribution of Java applications and applets. What the class loader does is it grabs pieces of code when it needs them. For example, when a program is running locally, i.e. on a single machine, it looks for pieces of code on its local hard drive or its local resources. If it can't find them, the class loader allows it to grab the pieces of code that it needs over the network. Let's talk a little bit more about the Java virtual machine. First of all, the Java virtual machine is a software implementation of a CPU. In other words, it's a program that somebody wrote to pretend to be a CPU. Now, the second thing, I want to talk a little bit about bytecode versus object code. Bytecode is the binary code that's run by this virtual CPU. Object code is compiled code that has been targeted to some physical CPU, such as a Motorola chip or a Pentium chip or a MIPS chip. Next thing I want to talk about is source code and class files. Source code, it looks much like C. It looks a little bit like C++. It's not exactly like either. And the source code is logically broken up into class files. Everything that becomes an object in Java is written as a class. And these files have a .class extension, so they're easy to recognize. Once they're compiled, every class that exists in the source code becomes an object, a single file that is then loaded into the Java virtual machine when the program is executed. Now, there's a couple of performance issues I want to talk about here. First of all, the fact that it is interpreted. These bytecode files are interpreted by this software implementation of a CPU, which means that at some point they have to be turned into native code to run on any hardware CPU, which causes a performance hit. A naive implementation of a Java virtual machine will run bytecode at about 20 times slower than compiled native code. You may think 20 times slower, that sounds pretty extreme, but on the other hand, when you have a scripting language such as C Shell or Perl or any of the popular scripting languages, some of these run 300 times slower than actual compiled native code. But a lot of this is going to go away with something called just-in-time compilers, or JITs. And what a just-in-time compiler does is it essentially finishes the compile. It takes Java bytecode and it compiles it into native code. There are some semantics involved there, such as the compiler, a just-in-time compiler doesn't just recompile the entire thing. It looks for parts that are computation expensive and finishes the compile for those parts for this native machine. So what that means is you have a little bit of a performance hit at load time, but we're all used to load time performance hits, such as when we're downloading code or even just starting a modern full-featured application. You notice that the splash screens are staying on longer and longer, so we're used to those load time performance hits, but it'll run much faster once the code starts executing. Now, we have, first of all, a piece of source code. Now, this source code, we're talking about the object code model here. This source code is compiled by a program called a compiler. The compiler takes this, it parses through the source code, and turns it into the binary representation for a particular CPU, often referred to as the target CPU. And this is just some binary code that represents the actual instructions of that physical CPU. Now let's take a look at the Java bytecode model. On the top of this diagram, we have the same thing. We have a source code. The source code looks like English, the same as we had in the previous model. We still have a compiler, which is the program that takes this source code and turns it into bytecode, which is the Java virtual machine language. Now, this is not platform specific. Basically, this compiler is the same in any development environment. Now, the next step we have is this layer between the compiler and the CPU, the interpreter. What the interpreter does is takes this bytecode, this Java code, and turns it into native CPU code. The interpreter is actually specific to different environments. The interpreter for an Intel machine is going to be different from the interpreter for a MIPS machine. So that's really where you get the homogeneous Java environment on a heterogeneous platform. Now let's take a quick step back. Java was originally developed for personal electronic devices, smart homes, intelligent devices. And unfortunately, that market never really took off. There was no interest in smart toasters. They tried to revive it with interactive television, and that never really happened either. And a lot of work went into developing this great programming language and this great runtime environment that ran on a lot of different devices. And they were really looking for a place to showcase all this work because it really was great stuff. Now, as we move ahead, we're going to talk about what really gave Java its start and really brought it into the limelight and where it is today. Let's talk a little bit now about the current technology and the emergence of Java. Now, about the same time that the interest in the personal electronic device and smart home market was dying came the birth of the web. It was originally commonly referred to as the information superhighway, which was on top of the internet, and here comes the web. This gave us a drastically different model of distributed applications. Essentially, we had web browsers as a window into databases, into new communications models, and this all ran on a heterogeneous environment. Essentially, everybody had different types of computers. This is a very server-heavy model. What that means is nearly every transaction requires interaction with some server. When you request a web page from a web browser, it actually asks some web server, some HTTP server, for this document, and the server gives you the document. So we have this new model of HTML for describing these web pages, for adding images and formatting text. We also had the Common Gateway Interface, or CGI, which was a means for communicating to another application, such as a search engine or some other type of database application. Now, if you think about this, a lot of these problems are similar to the problems that resulted in the original Java development, the heterogeneity, the network distribution. So the Java team looked at this as an opportunity to really showcase all the work that they had done in developing this new programming and runtime environment. So the way they did this is with a proof of concept called Hot Java. Now, Hot Java was really intended as a showcase for the Java language. What Hot Java was a web browser. It was similar to the then current browsers, Netscape Navigator or Mosaic, and it basically did the same things without all the bells and whistles. It was written entirely in Java, which is a proof that it is a full-featured programming language. If you can write a web browser in it, then you can write anything in it. Now, this proof of concept had one special property. It had the ability of downloading Java code and running it locally in your web browser, embedded with your HTML content. Now, this generated enormous interest. This was a very exciting thing. It didn't work that well. It was slower than the other browsers. It didn't have all the bells and whistles, but there was that spark just showing how intriguing it was to offload execution from a web server, put it on the client side so you have fast, scalable execution, and being able to do a lot of tricks that you just couldn't do in the HTML CGI model. So this quickly gained a lot of market acceptance and really generated a lot of interest in Java in general. So what you had was dynamic web documents. You had this client-side execution, which was embedded in a very similar way that an image is embedded in a web page. Now, this was not a replacement of static HTML. This was really an embellishment because it's intended to be embedded. It's intended to coexist with HTML. Let's talk a little bit about the difference between server rendering versus client rendering. In a CGI model, in the Common Gateway interface, you have an application that's sitting on a web server, and you have a browser that's communicating with it. Now, let's take a hypothetical application, a calendar. In that model, let's say the user requests a month view of their personal calendar. The server gets the request. It has to describe the entire result in HTML. It sends that entire HTML page back to the client, and the client's browser renders it. Now, all of that data you would think would be local. Say the user then wanted to look at the day view to see what their schedule was for one particular day in that month. You would think that the data would already be there, but in the CGI model, it requires another transaction with the server. Essentially, the user requests the day view, it's sent to this server, the CGI application is run, and a new page is described in HTML and sent and re-rendered by the client. This is a very inefficient model. Now, in the applet example, we could have that same application, this calendar application, running as an embedded application in this web browser, and all the data can be local. When you request the data from the server, it's all stored in memory. It renders it as a month view. When the user then clicks on something to see the day view, the data is just re-rendered locally, and no more server transactions are required. This is much more efficient. You're just re-rendering the local data. And one other thing that applets give you is HTML is a very limited model for describing any kind of interface. And Java gives you a very rich set of interface tools for doing button widgets, for doing graphical buttons, slide bars, radio buttons. It's a much richer model for developing client-side applications. So how does it work? First of all, when you have a Java application, you embed it using standard HTML code into an HTML document. Now, when a web browser accesses this HTML document, it parses through the HTML. It says, okay, there's an applet embedded here. Let me load it. It grabs the bytecode for that applet, and then it executes it on a virtual machine, a Java virtual machine. So the browser has its entire runtime environment included as part of itself. It's part of the browser application. And the browser knows how to load classes or the Java bytecodes from network resources, to load them from web servers. Let's have a quick definition of applets and talk about applets compared to applications. Java is often referred to in terms of applets. A lot of people have heard of Java applets. But that's unfortunate because Java really is a full-featured programming language, and you can write some really sophisticated applications, such as the hot Java browser. what an applet is in terms of this is an applet is a Java application that was written specifically to be embedded in an HTML document. In other words, it's an application that was designed to be run in a web browser. So we're going to move forward now and talk a little bit about how you embed applets in HTML documents. Let's talk now about embedded Java. When we talk about embedded Java, we're talking primarily about embedding applets in HTML. And the way this works is with HTML tags. First off, there's an applet tag. The applet tag surrounds, first of all, a set of parameter tags and then some optional HTML for support in older browsers. But first, let's talk about some of the required attributes for the applet tag. First of all, there's the code attribute. And the code attribute is what actually points to the applet bytecode or the class file. So this is followed by the name of your program. The second two things are required so that they can be placed correctly within an HTML document. These are the width and height attributes. Normally, these are in terms of pixels, but in some browsers, they can be in terms of percentages of the size of the browser window. Now, there are some optional applet tag attributes, the first one being the code base. And the code base is followed by a URL that points to where the actual class files for this applet exist. Essentially, the browser needs to be able to load these objects over the web, and this is telling it where to grab them from. Now, an archive attribute is a way of compressing a set of Java classes into one file. And this can be referred to with the archive attribute, and this is normally a zip file, which is a file format for these compressed files. The alt attribute is what I like to call a friendly gesture. What alt does is it allows you to specify an alternate string of text that will be displayed in the browser if the applet is unavailable or if the browser has had Java disabled. The name attribute is used for giving a unique identifying name to an applet so that you can have applet-to-applet communication. And finally, we have some alignment attributes. There's align, which can be either left, center, or right, which helps align the surrounding HTML elements with the applet. And there's a vspace and hspace attribute, which allow you to control the vertical and horizontal space around it. Now, in parameter tags, one of the nice properties that you have with Java is you can have a compiled program and give it parameters within an HTML document. So you can customize an application or an applet using solely HTML. You don't have to do a single bit of Java coding. And this is done with a param tag. A param tag has two attributes, namely the name attribute and the value attribute. And what you use these for is the name attribute gives the name of a particular parameter. Like, let's say we wanted to have an animation applet, and we wanted to have a parameter called loop. And the loop parameter told you whether the animation would keep looping or run through once and quit. So we'd have a name equals loop, and the value could be true or false, giving a value to that attribute. And all of these are accessible from the applet and are written in the applet code. So the only way you, as a person using an applet, knows what these parameters are is either by being told from the programmer through some sort of documentation what the parameters are, or by having access to the source code. So now, just support for older browsers, there's the problem, what do you do if your applet is trying to run in a browser that doesn't support it? Well, one of the nice properties of HTML in general is that browsers will ignore tags that they don't understand. So an old browser will ignore the applet tags, will ignore the parameter tags, but then you can insert arbitrary HTML between the begin applet tag and the end applet tag. So an applet-enabled browser will ignore this arbitrary HTML. It's only looking for parameter tags, param tags. And any old browser won't understand any of the other stuff, so it'll just print out the HTML. So let's look. Here is just a sample embedded applet. you notice that we have the applet tag. We have a Java file called foo.class. That would actually be our applet. The code base, http://foo.com, that would be the network address that this Java applet was loaded from. We gave it a width of 100 pixels, a height of 200 pixels, an alternate string of text that would be displayed if applet support was turned off in your browser. We have this string of text following saying old browser support. That can be any arbitrary text or HTML markup that'll be displayed if the browser doesn't understand applets. Finally, we have a single parameter in that param tag. We gave the parameter name of text and a value of hello, which would just be a way of giving this information to the applet. So to summarize, an applet is embedded in an HTML document using HTML tags. It's very simple to embed an applet and to supply parameters so that you can customize an applet without ever having to do any recoding. Let's talk now about using pre-compiled applets. We talked briefly about how to use HTML to embed applets. Now, let's talk about how to use applets that you find. First of all, you need to find the code base. If you look at a web page that has an embedded applet, look at the source code. Use the view source mechanism in your browser. Find the code base. That'll tell you the URL that this applet is being loaded from. You can determine the necessary parameters by just looking at the param tags in the HTML source and figuring out what the values are to the names and customize that yourself. And then finally, you just write your own HTML to access it. You wrap your HTML around this applet using the code base and the name of the code that you found from another web page. So some example applets. I want to talk first of all about a very simple one, just for adding sound to a web page. What this allows you to configure in the HTML are the interface. I'm going to talk about the HTML code for the parameters, and we're going to look briefly at the Java code. Okay, here we have a simple applet embedded in an HTML document that plays sound clips. It allows you to load a clip over the web, and here we have a simple interface for starting or stopping the sound clip. So let's just take a look really quickly at how this is embedded. First of all, the applet code here, it has these parameters that we talked about earlier, the code that points towards the actual binary code, the code base, which lists the URL that this is being loaded from, a width and height, and the more interesting part is here's where the parameters are listed. Basically, there's a parameter for the URL to grab a sound from. There's a parameter that tells it to start on load, a parameter that tells it not to start on exit. And essentially, these are the names and values of these different parameters that allow you to customize this applet. Now let's quickly look at the code, the Java source code for this. And in the Java source code, we look down here and we have a bunch of code here that says get parameter. And the get parameter is looking for a parameter called, in this case, start on load. So the only thing that's really important is that there's a correlation between this name here, start on load, and the name that we gave the parameter in the HTML code. So now let's look at a little bit more sophisticated of an applet. This one is a calendaring application. It's a full-featured application that just happens to run as an applet in a web browser. We're going to take a look at the interface and really show you what a full-featured applet can look like. This applet here is running entirely within Netscape Navigator. And as you see, we have a really rich set of features here. We have a number of interfaces here for accessing data in different ways, and there's no network transactions that are happening as you would have in a CGI model. Basically, I wanted to show that you can have very sophisticated applications that are programmed as applets and embedded in web pages. So now you know how to incorporate applets that you found on the web. Where do you look for them? Let's talk briefly about finding applets. First of all, one of the largest repositories of Java source code, applets, JavaScript, you name it, is at the Gamelon site, www.gamelon.com. A lot of information, publicly available source code, as well as applets that you could just embed into your applications. Second of all, go straight to the source, Javasoft. www.javasoft.com has a lot of information, white papers, a lot of things about finding demonstrations of different types of applets. And last of all, I have at my website a list of demonstration applets that you can also incorporate into your own web documents. There's a lot of places that you can look for applets, and it's very simple to incorporate these into your own applications, into your own web pages, into your own intranets. One of the biggest issues with network distributed code are issues of security. Some of the problems that you have with security are network access. When you have code that came from an anonymous source running on your machine, you don't want it to have arbitrary network access because it can start doing things in your name. It can start trying to break into somebody else's system or send malicious email that'll be traceable to you. Also, there's problems with file system access. You don't want some programmer, some anonymous person to write some code that gets loaded on your machine and starts poking around at your file system, or even worse, causing problems, deleting files, formatting hard disks. So to address these problems, Java has what is called a security manager. And security managers allow you to set a security overview to allow or disallow access to certain resources. And these are configurable in the runtime environment. Now, security managers in general are sort of a binary switch. You either turn it on or turn it off. But what you really want is the ability to configure security managers depending on where the code is coming from. So you have this idea of digital signatures. And digital signatures are a way of adding a signature to an applet, which would be referred to as a signed applet, that guarantees that that applet came from an individual, the person with the signature. So I would apply my digital signature to an applet, and when you loaded that, you would know that it came from me. And you could adjust a security manager based on that. Say you trust me, you may allow me to have file system access since you know that it came from me. Whereas in general, if it's a digital signature from somebody that you don't know or don't trust, you may disallow this access. So the security manager also, it deals with code in two different ways. We have the notion of trusted and untrusted code. Now, trusted code in general is code that's coming from your local machine. The system assumes that if the code's actually coming from your local machine, that you knew what you were doing when you put it there, so it's trusted code. Whereas anything that's loaded over the network is generally untrusted. And what happens is trusted code is generally not verified, so you don't have the overload, the overhead of running the bytecode verifier on trusted code, whereas untrusted code is always forced to go through the verifier. So let's look quickly at the relationship of Java source code, of the Java language, with other languages. Java is not a superset of C++, it's not a superset of C, but it borrows heavily from both of these and has a lot of the same properties. But it is a different language. There are things that you can do in C that you can't do in Java, there are things you can do in C++, and there are things in Java that you can't do in either of those. So now, for the class files, all Java source is divided either into classes or into interfaces. And an interface is really just an abstraction of a class. And in classes, you have normal or abstract classes. A normal is what you use to create an object in Java. Any object is a normal Java class. Now, an abstract class is a class that is meant to be subclassed, essentially a template for developers to create new objects based on some set of parameters that you've defined in an abstract class. Now, an interface is very similar to an abstract class, except an interface essentially defines a contract with a programmer. It lists a set of methods or procedures that you guarantee to implement in your code when you implement this interface. So it allows a well-defined interface into your code. In the Java inheritance model, we have a linear inheritance. In other words, you can have a class A that extends B, and you can have a class C that extends B, but you can't have a class C that extends both A and B. It has to do it in a linear progression. But any class can implement an arbitrary number of interfaces, which are these contracts. So you have a well-defined set of interfaces, so you know how to interact with these objects that implement these interfaces. Let's look quickly at a simple class. It starts with the keyword class. You give it a name, such as my class, and then the class body is delineated with curly braces. And within these curly braces, you can have a set of fields or methods. Methods are the term for procedures in Java. The fields have a number of properties. They can either be static, meaning that you have one field amongst all instances of a class. The default is to be an instance variable, meaning that each class has its own instance of this field. You also have access protection. You have a public field, a private field, a protected field, which just allows access from other classes. And you also have a transient keyword. And the transient keyword is used to flag a field that should not send its data if that object migrates to another machine. Now let's talk briefly about methods. Methods are almost exactly the same as a procedure in C or C++. They must define a return type. They have a body that's also delineated with curly braces and can define they have mathematical statements or basically any language constructs. All of your work happens in your methods. Now typing, this is an important thing in Java because Java is a very heavily typed language. And one of the nice things about this is that it gets rid of a lot of semantic errors. Basically, you can have things in other languages that are loosely typed that are not syntactic errors, but are semantic errors, meaning you meant to do something else, but it still compiles. It didn't mind that you're using two different types. It has a very well-defined casting and conversion system for casting from one type to another that's actually very strict. And one other thing is you have a well-defined and simple set of type sizes. So you know that an integer is always 32 bits wide. You know that it's always big-endian byte ordering. In the Java object model, you're allowed to do things such as method overloading. In other words, you can have a method that's redefined for different sets of parameters. You also have method overriding, which allows you to redefine a method that was defined in a superclass. In other words, if a method is defined in one class, a class that extends that class can redefine that method. Constructors are essentially methods with one exception. They have no return type. Other than that, they have all of the same properties. They can be overloaded, overridden. They also have access to superclass constructors. The method structure starts with a type. That's the return type, or the object type of this method. You give the method a name, and then a set of parameters that are within parentheses. The body of a method is within curly braces and contains a set of algorithms, basically the workhorse of your application, and a return type. Statement separators are exactly the same as in C or C++, semicolons. And you have a notion of global versus local variables by simply defining a field as being static and public. So you've defined a field so that it's accessible via anything, in other words, public, and static, meaning you only have one for an entire set of objects. Java supports dynamic binding, which means that class files are bound late at runtime. That means that when an application is running, it only needs to load the parts that are part of what it's doing at that time. In other words, a single application can be made up of a whole set of objects, and it'll just load them as they need them. So that means that an object can be updated as the program is running as long as it hasn't been loaded yet. So to compile the source code, the easiest way is to grab the Java development kit from Javasoft. The Java Development Kit has a number of applications, one, the most important of which is the Java compiler, or JavaC. And JavaC essentially will take a Java source code and compile that and turn it into the Java bytecode format. A couple of the other applications that you get with the development kit are JavaDoc, which is a really nice application for automatically generating documentation for your application. And also you have Java, which is the interpreter. That is the standalone Java virtual machine, the Java runtime environment that makes this all work. Now the object code, first of all, you take the source code, the .java files, and you compile that into .class files. And that is a hard and fast rule. The source codes are .java, the object class files are .class, whether they're interfaces or abstract classes or anything else. So there are a number of development environments out there. There's Mojo, Cathay, Visual J++. There's a lot of options that have integrated development environments, that have these compilers built into them. There's a lot of things that you can grab commercially and free, such as the Java Development Kit, for developing your Java applications. One of the really exciting things about Java technology are the directions that it's taking in the future. One of the technologies that really stand out here is the Java Beans architecture. Java Beans is a component architecture. It allows programmers to create these component objects that have well-defined ways of interacting and communicating with each other. And what this facilitates is the ability to create applications in visual programming environments such as Visual Basic or J++. It allows programmers to take these predefined objects, drag them together, create little links to them, and set parameters with simple dialog boxes. And the application framework is another part of this, which allows institutions or programmers to create their own looks and feels for these component architectures. Other future developments are the distributed computing facilities that have been built into Java, such as remote method invocation, RMI, which is a Java-specific way of doing distributed objects, or IDL, which is the interface description language, which goes right along with Corba and IIOP, which are the standard object request brokerage architectures that have basically been embraced by the industry. So other interesting things for Java in the future is Java is being deployed as an operating environment for smart cards. It's being used as a connectivity vehicle to databases using the JDBC classes, the Java database connectivity classes. And it's also very popular in IS departments because it allows them to support a single platform for their entire organization, which will usually run on a number of different types of computers. So where is the JVM been adopted? A lot of people wonder, where is the virtual machine? Well, the virtual machine has been ported by Netscape in their Navigator products and their Communicator products. It's also been embraced by Microsoft, both in Internet Explorer, which is their browser, as well as Microsoft Windows. You have a number of Java virtual machine runtime environments for pretty much every platform right now. And the really hot things coming down the pipe are the just-in-time compilers. You have those from Borland, you have those from Microsoft, you have a number of industry leaders that have started to use this. And then one other really interesting thing about the future of Java is PicoJava and hardware accelerators. Java has basically gone backwards. It started as a virtual CPU and is now being printed in silicon. So you have these Java chips that are now Java machines instead of Java virtual machines, which have the ability to run much faster than the Java virtual machine, which is interpreting the code. So as you can see, Java gives us today an amazing facility for developing applications, for deploying intranet applications. It's an amazing time right now. And in the future, we see a lot of very interesting and intriguing things coming down the pipe, such as the network distribution model, such as the interactivity, connectivity with legacy databases. It's a very exciting time, and it's only going to grow. So let's take a break now and go over some review questions to see if we've really gained an understanding of where Java came from, what Java is, and where it's going. What is the difference between source code portability and object code portability? Well, source code portability refers to the portability of the source that needs to be recompiled for different platforms, where object code portability means it's been compiled once and will run on a number of different platforms. List 3 characteristics of Java that provide language-based security. Could have answered any 3 of the following. Memory access restrictions. It's a strongly typed language. You have a configurable security manager. There's a bytecode verifier. What are the 3 components of the Java runtime environment? There's the interpreter, the verifier, and the class loader. What is the difference between a Java applet and a Java application? Simply stated, a Java applet is an application that was meant to be embedded in an HTML document and run in a web browser. List 2 advantages of using an embedded client-side applet as opposed to a CGI model. One advantage is that an applet can have local data and doesn't require a server transaction to re-render data. Another advantage is you have a much richer set of GUI tools in an applet model. Can an applet access network services on a machine other than the one from which it was downloaded? Not by default, but a security manager can be configured to allow network access to an applet. Well, thanks for watching. I hope you have a firm understanding of what Java is all about, what you can do with it, and what's coming down the pipe. If you need to get a hold of me, if you want to have any questions about the program or just want to chat, feel free to send me email at downing@webcal.com.